So, hi everybody. Welcome to our weekly seminar at the Institute of Astrophysics in Crete. Today we have the pleasure to have with us Dr. Pratik Dabhade. So briefly about Dr. Dabhade, he is currently a postdoctoral fellow at the Astrophysics Division of the National Center for Nuclear Research in Warsaw, in Poland. And prior to this, he held a postdoctoral position at the Instituto de Astrofísica de Canaria in Tenerife and also at the Paris Observatory in France. He completed his PhD at the Leiden University in the Netherlands in early 2021. And Dr. Dabhade is specialized in the use of radio continuum data to study various extragalactic objects, including active galaxy, galaxy cluster, and galaxies. He's also an active member of the SKA Continuum Science Working Group, and he is the PI of the SAGAN project, which aims to explore and understand the giant radio galaxies, and this will also be the focus of today's talk. So thanks for being with us. The floor is yours.
Okay, thank you. Thank you all for inviting me and giving me this chance to present and discuss with you all the work. So yeah, let's begin. So you all must be very familiar with this part of the spectrum, the optical wavelengths. This is how the sky looks in the optical light, which all of you must have seen. And some of you or many of you must have seen that at radio wavelengths, the sky looks quite different. And each of these point sources, what you see on the screen, is a black hole, a supermassive black hole giving out jets, except for the big shell which you see towards the right side, that's a supernova remnant. So before I dwell into the topic, let's go through some basics of radio galaxy. Some of you may be aware, some of you may not be aware. So let's begin. So this is how a typical galaxy looks in optical, which spans around 20 to 60 kiloparsec, depending on the morphological type. And a typical radio galaxy has these characteristics, where AGN sitting at the center of the galaxy, host galaxy, is producing these massive bipolar jets seen at radio wavelengths, and these jets go on to create massive lobes which terminate with hotspots. So typically this type of radio galaxy is called FR2, named after Fanaraf and Riley, where you have edge brightened emission in the radio spectrum. And this is a simulation showing how the jets propagate as a function of time and distance. You can see that they can create all sort of instabilities, or the plasma, we can see the hints of plasma instabilities. And then after a point, if the jets switch off, we don't really see the prominent hotspot as we saw in the previous example. But this is just to give you an idea how propagation happens. And like I said, the radio emission is from synchrotron mechanism, which all of you may be well aware of. So I will not spend time on this. And radio galaxies come in very various shapes and sizes. And depending on their properties, we often label them into these categories, where the wide angle and the narrow angle tailed radio galaxies are mostly associated with galaxy clusters, where these host galaxies are actually infalling towards the galaxy center and thereby causing this peculiar shape. And the restarted ones are called the DDRG. So I'll talk about it in the later half of my talk. And but the main topic for the seminar are the giant radio galaxies, which are the larger or megaparsec scale versions of normal sized radio galaxies. So before I delve more into the giants, let's go through some basics of importance of image resolution. So what you see is NRO VLA Sky Survey at 1.4 gigahertz. This is a radio continuum image with 45 arcsecond resolution, and you see a bright blob, which we can't discern anything about its morphology. But if the same object is observed at a much higher resolution, then you see that okay, there is we see the actual structure. We see extended radio emission, which is prominently bright in the towards the south. However, if we go much into much finer with the finer resolution than 5 arcsecond, you see that the source which seemingly seem one, it is split into two. Now, still, it doesn't give us the complete picture that what is really happening. Is it radio galaxy? Are there two radio galaxies which are probably infalling? We don't know, and that is where the importance of multi-wavelength comes into play. Because just with the radio image, you're kind of half blind, and that's why we need to always overlay and check the optical counterparts. So what we see that indeed it is one radio source, it is one single object. So on the left, you see the radio emission in blue. So it is a tailed radio galaxy, which is probably infalling. It doesn't strictly fall into the wide angle or the narrow angle, but it is surely moving towards the cluster center because of its peculiar morphology. So in when for radio galaxies you need deep high resolution radio images as well as the multi-wavelength optical IR to really discern the some signs. So now coming to giant radio galaxies. So giant radio galaxies, like I said, are the megaparsec counterparts of normal sized radio galaxy. On the right, you can see size diagram where you can see how our Milky Way fares in comparison with the famous Cygnus A radio galaxy and how the giants are, how big they really are. So they are traditionally classified as RGs greater than 700 kiloparsec. They are at times also hosted by a very powerful agent called the quasars, and nearly 30% of the population, known population, is hosted by them. Naturally, they have the largest astrophysical jets. So you have this central engine, the supermassive black hole, giving out these bipolar jets, and they can scale sizes of megaparsec at times. The overall sizes of these giant radio galaxy uh, spans more than a galaxy cluster size or comparable to the galaxy cluster size. So towards the end, I have a surprise on this end that is 5 megaparsec the limit or not? We'll find out. And they're mostly hosted by giant ellipticals and very, very rarely with spiral shaped. And from radio data, we can, using the spectral aging analysis, we can give an estimate that how long this radio galaxy has been active for. It is not a super accurate method to determine the actual age of the galaxy, but it actually tells you how long the emission has been present or how long that activity is going on from just the radio data. But that has been limited to very handful GRGs because we require enormous amount of multi-frequency radio data to do that kind of analysis. So just to give you another example, that 1 megaparsec is actually more than 30 Milky Way galaxies. So you understand the sheer size of these sources is not normal. They are extremely large, very abnormal, and you can see how they fare with other famous galaxies and radio galaxies. So historically, these were discovered in the 1970s, early 1970s, and these two galaxies were discovered with the Westerbork radio telescope in the Netherlands, and you can see these contour radio maps. And today, of course, we have much better data for them, and we see much more finer detail. So it has been nearly 50 years since then. So, like I said, these have the largest astrophysical jets, but why do we care about them? Why should we study them? Why are they so special? So, because we are still trying to understand why they are so big. How do they grow to such a large extent? How are they formed? Are they really rare compared to radio galaxies? Are they the end point of the radio galaxy evolution? And since their sizes are so big, do they contribute to other astrophysical processes? Because since they are megaparsec scale objects, they can pierce through the intergalactic medium and actually do seeding of magnetic field. They are capable, but actually, do they do that? So that is something which we want to understand. One of the proposed hypothesis is that perhaps they are continuously restarted AGNs, which allow them to sustain the activity and grow large. And we also want to. They also provide us the biggest astrophysical lab to study plasma physics, because clearly these jets are they're stable for such a long period and size. So what allows them to do so? So this is a perfect lab for studying them. So the major hypothesis which has been proposed in the last 30 years to um, understand or to explain why these giants are big is because perhaps they're hosted. This is the most obvious, that perhaps they are hosted by a very powerful AGN, or another obvious thing is, oh, they only grow in sparse environment, which the jets and the lobes do not have any hindrance in for their growth, or perhaps it's a combination of two. Now, this was proposed, of course, but only handful GRGs were known back then in the 90s, 80s, and the things started to change around 2000s when the sample grew larger to 50 and 100. But again, that is not enough, and also we need multivalent data to really probe their AGN properties. So, like I said, this is what the state of the art was back in 2016 when I started this project called Sagan. Only about 300 or so were known, and that is after nearly 40 years of 40 years since its initial discovery. And that was due to lack of deeper radio surveys and optical multivalent and other multivalent data. And that's where my project came, Sagan, which is an acronym to this great scientist, but nothing to do with him. It is actually search and analysis of giant radio galaxies with associated nuclei. And the objectives were very clear, that we want to first make a database of known GRGs, find more GRGs, then acquire multivalent data and carry out uh, their studies. So the way to do it was using newer surveys which were available, which were getting available back then, and then obtain their optical data for redshift and AGN properties. Eventually, study their fueling with millimeter wave observations using CO data from IRAM, NOIMA, or ALMA, and again to study their environment to test the hypothesis. So this was the initial plan. This is with these goals we started this project, and these are some of the telescopes which we have used along the way. So like I said, the first was make a complete compilation. Now that task was for the known GRGs, okay, and that task was very difficult because since this nobody carried out the study in a very uniform way. People had different names for them since the 1970s, so it was not easy to just search with giant radio galaxies. Uh, Different types of resolution data, as well as the sensitivity of the data, meant that we had to recheck some of the sources because some of them were not genuine giants. And also, if you recall that in the 70s, 80s, and even 90s, the value of Hubble constant, the H naught, was not fixed, or let's call it, it wasn't close to what we have today. People used all sort of H naught values from 50 to 100, which meant that the co-moving distance changed, and without co-moving distance we can't really measure the sizes of these giants. So basically that's what meant that's what was meant, that we needed to take all the sources, we needed to verify their structure with neo data, and then construct the catalog uniformly so that we don't have any erroneous sources. So this took quite a lot of time, but it was rewarding. And next was to search from the available radio surveys back then, and see if we can grow the sample, not just rely on what we had discovered in the past 40 years. So how do we get the sample? Is of course take the radio data, optical data, and you need to overlay them and look for extended objects, but that's not easy. So, like I said, the radio data can be quite rewarding, and we can use multiple of them as complementary to each other, because some of them cover a lot of sky, some of them cover small part of the sky, but they are very high resolution. So you have to. There are trade-offs in using them, but we can use multiple of them if they are present in the same part of the sky, and then take the best of all worlds to do our science. So here is an example how one goes about searching. So this, what you see, is a radio image, and one had to scan through this back in like 8 9 years ago, because we didn't have ML or AI tools back then to start doing this in an automated fashion. A quick note: even today, this is not fully automated. It is still a work in progress. We still have to do manual job, so it is time consuming and tedious. So coming back to the image, you can see there is clearly one extended object which was easy to spot because it was almost 20 arc minutes. We can see it's towards the south, and then it indeed turned out to be quite big. And more interestingly, it was hosted by a spiral galaxy. So, uh, side note that only 5 to 10 objects are known. Radio galaxies are known with spiral host, but I just chose this example to show you because this is 20 arc minutes in angular size, so it is easy to spot in a big radio image. But not all of them are so big. Some are small size, but they are distant. So you have to look for all the extended sources. So around 2017, 2018, we started getting the first deep radio data from the LOFAR 2-meter sky survey. The first radio survey at around 150 megahertz, giving unprecedented sensitivity with high resolution. And with just 424 square degree, we obtained the largest sample of giants back then. So you can see that we almost doubled the population uh, of the known giants with it. But this was, of course, very tedious, like I mentioned, because 424 square degrees is quite big, and one had to go through every inch of this radio sky to look for these giants, and then similarly do this process in optical to look at their host properties. This is again from not from LOTS but from NVSS, where we used multiple different radio surveys to establish a second big sample as part of this project, and that eventually led us to create this big catalog of 820 around 800 sources of giants. So our first step was realized here, that we now have not just 300 but almost 1,000 sources uh, for which we can now acquire multi-wavelength data to study their host properties, to understand that are their AGNs really exceptional to grow these radio galaxies to large scale. And yeah, so the way forward was get multi-element data, all what is available, to estimate the properties you see on the screen. So you need to, since it's a radio galaxy, you need to measure its flux at all available frequencies to see what is their luminosities, how powerful they are. Spectral index is a measure that if the radio plasma is relatively new or old. So you can do that when you have two radio frequency data. Depending on the resolution of the radio data available, we can classify them into various radio categories like FR1, FR2, or the restarted ones or hybrid ones. We can estimate that time averaged jet kinetic power, that how powerful these jets are possibly, and then the hardcore AGN properties like black hole mass, the Eddington ratio, the accretion rate, and if the AGNs are high excitation or low excitation. So all that was possible with SDSS wise data. That is what we tried to do. So I'll quickly show you some of the results. So we not only computed the black hole mass using the M sigma relation, which is not the super accurate way, but it is still an estimate of the black hole mass. So we not only did it for giants, but we also made a sample of normal sized radio galaxy to see if the properties differ with them. The normal sized radio galaxy, the statistics, the population is quite largely known because they are not that rare compared to giants. So you can see the difference in the stats. But on a statistical level, the properties seem to be very similar. The statistical distribution seem very similar in terms of black hole mass and the accretion rate for radio galaxies and the giant radio galaxies. Then we devised, since we didn't have spectroscopic data for all of them, but we did have WISE mid-infrared magnitudes, which allow us to do this color diagram analysis, which has been calibrated using spectroscopic data that various AGN types or star-forming galaxies lie in different parts of this color plot. So the region one is populated with quasars and high excitation regions. High excitation AGNs, which show prominent spectroscopic emission line, broad lines. Region 2 is mainly very low excitation AGNs. Region 3 is low excitation plus star forming, and region 4 is star burst or ultra luminous infrared galaxies. So as evident from this plot, we found that majority of them were low excitation radio galaxies, and of course, a significant fraction is high, but the majority was. So we didn't have a very clear result. GRGs, we concluded that they don't have a preferred AGN state. But my hypothesis is that the GRGs do start in high excitation, but eventually, as the time elapses, they progress or they evolve into the low excitation, depending on the availability of the fuel, gas fuel available to the AGN. Then again, we distributed our sample into high excitation radio galaxies, low excitation radio galaxies, and to see if within these two categories do we see any difference. So with respect to the accretion rate, which is expected, the high excitation showed the higher accretion rate. The jet power was higher, the radio power was higher, but with respect to the size, there was not much difference. Then we also touched upon the environment of these to understand that do they only grow in sparse environment? Is that the only very obvious reason for them? But we did not have X-ray data, but we have the next best thing. We have galaxy cluster catalogs, which allowed us to spatially check whether these giants are associated inside a galaxy cluster. So we did this and we found around 15 to 20 are right at the center. 15 to 20% of our sample are right at the center of galaxy clusters, which are obviously very dense, and hence the sparse environment theory did not hold true. That clearly there is a significant population which is growing inside dense galaxy cluster environment. So there is something surely more there. So on the plot on the right, you can see the mass distribution of the galaxy clusters. The GRGs are indeed avoiding the most massive ones, but still, 10, it is still found in 10 to 14 Emerson galaxy clusters, which is not a small number. So, like I said, we also wanted to study its fueling properties, the Aegean fueling property, what is the fraction of cold molecular gas, and we found evidence only in two sources where there is CO, cold molecular gas detected. But those two galaxies were biased because those two were spiral. So naturally we found them, but for the rest of the 10 or 11 elliptical galaxies, we did not find, which is expected. So this result clearly showed that they are deficient in star formation. There is no special property for their elliptical host galaxy. This was um, expected but not shown. So that is the importance of observing them and then disproving. So here's a quick overview of the Sagan project, where we found big samples and studied them using multivariate data. There is also a review which I wrote, which was published last year, comprising 50 years. So you can find all the details there. Anyway, so I'll progress ahead to um, some individual sources which can be rewarding to study, because so far the study was focused on sample studies that we find large sample, do a statistical study, but at times there are some sources we've come across which need in-depth analysis. So this is a 45 arc second image, 45 arc second radio image of a peculiar giant radio galaxy, where it seemed like a radio galaxy, but you see these multiple components north south, which were confusing. And then there is a white colored blob which is sitting there. So we did not know what to do. So obviously we wanted higher resolution, and we did not have higher resolution from any other survey. So we have to carry out using our own dedicated observation. So we needed to write a proposal with GMRT, which is a telescope in India, with to give us higher resolution images. And when we attempt to do this, especially as a PhD student, we think we are going to find something remarkable, which will allow us to publish in Nature. But there is something which is a big problem in radio astronomy, that is called the radio frequency interference, which at times can cause havoc. So here I'm showing you an example of how the band, the frequency, this is basically frequency versus amplitude, and this is a well-behaved observation with the spikes as RFI, which is okay. We can read them out, but at times you are handed this where there is a hint of data in a sea of RFI, and you can't do science then. But that happens at times, so that is how things are. And this is getting worse with the Starlink, so we have to do something about it. Anyways, once we get the data, now we are ready to process it, and then that's where the rewarding time comes in. So you can see uh, that particular source actually turned out to be not only a giant radio galaxy, but that white bright spot was a kink. This is a plasma instability. Not only we proved that this is a giant radio galaxy, but we found one of the largest jets, around 280 kiloparsec, bipolar jets, which are very well mapped with the GMRT with at various resolution. But this plasma instability, which are found commonly in astrophysics, but not at this scale, because the kink, what you see here, the omega shape, is nearly 100 kiloparsec. So three Milky Way galaxies can fit into it. And we only have hypothesis at this moment that this could be some sort of Rayleigh-Taylor instability or Kelvin-Helmholtz instability, but those have been seen at very, very small scale, like parsec scale, or few kiloparsec at most. But 100 kiloparsec we don't. So we are in talks with some MSD simulation experts who can help us with explaining how such an instability can be caused. So this becomes a astrophysical lab for studying high energy plasma processes and their interaction with the environment. So this is just a multi-wavelength view of it. The red, blue being radio and the background particle in yellow. So the main highlights um, Project Sagan are that GRGs, they are not as rare as we thought back in 2016, because now we have found a big sample, but they are still rarer compared to normal size radio galaxies. Their AGNs can have both low and high accretion mode. Uh, so there is no exceptional AGN at the moment they exhibit, which is allowing them to, grow these jets or launch these jets. They are quenching the star formation in the host galaxy. Um, I haven't talked about the Sagan 4 yet, which will come next, but it is also an probe and environment, and GRGs as probes of astrophysical processes. Spectral ages, like I mentioned at the start, are very hard to do so, but there are a few groups which are pursuing this, and we'll have soon results pertaining to it, that which will show us that are they really the older counterparts or not. So in the recent times, the LOFAR surveys that came out with their data release too, which uh, found not just few hundred, but almost 2,000 new giant radio galaxies, which has taken the overall GRG landscape to now nearly 4 to 5,000 sources. So we've come a long way, and it has become a hot topic compared to 8 years ago. And you can see how it has skyrocketed after 2016, 2018 with the uh, advent of these new sky surveys. So you can see the big increment, and that has started around 2016. And when we started this project, our initial few result, and then now every radio survey is reporting them in large numbers. Okay, so I said I would touch upon the restarted activity because that is one of the again proposed hypothesis that these radio galaxies are continuously undergoing rejuvenation at the AGN level, which allows them to keep on producing these jets. Um, and uh, as a part of this study, we discovered a radio AGN with 3 episodes of activity. Two are known for 20-25 years. Two levels of activity are known, but three are extremely rare. So only three were known prior to our discovery. And this is how it's called a triple radio galaxy, where you have three sets of radio doubles. That So at the center you have a radio core, then you have the jets which create this hotspot, and those are lobes. So you have three sets of lobes. So this was first discovered in 2007, and we discovered the fourth one using again LOFAR, uh, and all these four triple double radio galaxies are giant in nature naturally, because there is a plasma which is extending outwards. So to test this hypothesis that uh, are they simply restarted, are they regularly restarted, we took a sample of giants and we tried to check how many of them show these signs of restarted activity in terms of morphology, like DDRG, double double radio galaxies. And that's the fifth part of the uh, Sagar project. And we found that that fraction is not large. It's around 3%. And we didn't know this prior. So morphological signs of restarted activity is only one way of identifying if the agent has restarted, but it is relatively obvious and easy to find because the morphology shows so. So this was first attempt and of course, the DDRGs as such are only 200 or so known. So we also increase that sample to understand, because you can study the first set of activity and the latest set of activity, their properties, and estimate the duty cycle of the AGN. Okay, so how efficiently it is doing it. So that's why it is important to study them in detail. So now I'll come to one of very exciting results which we found in the recent times. So to begin with, we started to probe the environment. We had better galaxy cluster catalogs. We had supercluster catalogs. So we asked ourselves a question that, okay, let us check what are the different environments in which GRGs grow. We started with the supercluster catalog. So we took supercluster catalog, we took our giant catalog, giant GRG catalog, and then we started locating them spatially inside superclusters. And also within superclusters, there are individual galaxy clusters. So we studied them inside galaxy clusters, outside galaxy clusters, inside a supercluster, and we accurately quantified that what fraction of them are in superclusters and what fraction are in non-supercluster and non-galaxy cluster environment. So earlier we could only say that 15 to 20%, but now we know that it is much more. It is nearly 24% of giants in dense galaxy cluster environment, and within those, 5% are in supercluster environment. But as we were doing this study, we had an idea that if we are able to locate these giant radio galaxy behind a supercluster, and if they are polarized, we can actually try and estimate the magnetic field of the intra supercluster environment. So this is based on the Faraday rotation method. So basically, uh, this is undergrad physics or high school physics, that you have a magneto-ionic medium and you have a polarized light passing through it. The magneto-ionic medium is going to rotate the polarization angles, and that rotation is what we are going to see. So basically, the supercluster will act as a Faraday screen. The background GRG with its polarized light is going to intersect this magneto-ionic medium inside the supercluster and is going to rotate it. And we have the rotation measures. Then we subtract it from the galactic contribution, because our galaxy has a magnetic field which further causes the signal to be rotated. So we have now mapped and modeled it well, so we can remove its contribution, and we get a small fraction of change in this rotation measures that allows us to estimate the magnetic field. And we were able to estimate around sub-micro Gauss level, which is um, which is in how do I put it, in agreement with certain theoretical model, but it is not in agreement with certain theoretical model. So that, but we did this as a proof of concept study. So we are now growing this study to bigger samples. But this was like one of the first big large scale use of GRGs as probes of other processes, like I mentioned. So now this is just going to be getting better with SKA, because we're going to find more of these sources, more polarized light, and but it's the question of probing how we can probe the environment, because we can extrapolate this to clusters, voids, filaments, and such. Anyways, so now that we have acquired a lot of data, we need to also get its spectral ages, and for that, to understand how old they are, and for that we require multi-frequency radio data from various telescopes. Uh, we can also study them at very high resolution, that their very core properties, to understand what is really happening. But before that, I'll come to our results with GMRT. So we did this first observational campaign with GMRT over 50 hours of data of a large sample of GRGs, which allows us to really nail down their morphologies, to detect and study the large scale jets, detect the instabilities, like I mentioned before, like I showed before, and study the factors for there, and of course get spectral ages. For that, we require a lot more data, but this is the first step towards realizing that. And of course, we can study the shocks which are there at the hotspots because of the high energy nature of these processes. So this is how we do it. This is an example. This is one giant radio galaxies. Based on the resolution, we extract various we extract spectrum, multi-frequency spectrum from various parts of these sources, and fit our spectral aging model and understand that which part is oldest, which part is the youngest. And now we need to do this for large sample to get a range of values. So here you can see it's mostly around 50 to 30 mega years, which is similar to radio galaxies. So far we don't see an exceptional evidence to say that they are really old. Then VLBI. So what is VLBI? Very long baseline interferometry. So you must have seen the great, amazing images coming from the Event Horizon Telescope of M87, which has mapped the shadow of the black hole and such. So those same set of telescopes can also observe other targets, but of course they can't resolve um, their event horizon in a way, because these objects are much fainter and farther out. But we can do so to understand what is really happening at the really core level, because we can see the signs of restarted activity. We can see we can actually estimate the inclination of these jets, because what we see is 2D, but this can give us an indicator of the 3D of the possible 3D measurements. And this has been largely unexplored. So we started this to explore what is possible. So this is still a work in progress, and hope to publish this soon. This is again one of the shortcomings, but there are HDSS, the Sloan Digital Sky Survey gives us lots of spectra which are useful, but there are parts of the sky, or there are some object selection biases which doesn't give you spectra of all the sources. So we have to carry out our own set of observations, and no big telescope is going to give you time to just measure the redshift. So we did our best to write a convincing proposal and spend several nights observing and getting some spectra. Because without redshift, we don't have the co-moving distance and we can't measure the size. So this is a working progress with a collaborator in Poland itself. There is much more uh, work coming out of this, which will be shown in future. So the GRGs have, like I promised, do they really grow up to 5? No, they don't. Now this is a result just from last month, which appeared in the main Nature journal, and it was so much so exciting that it is on the cover of Nature. And because it is, they found a giant 7 megaparsec in size, which is bigger than the most massive galaxy clusters. And that was possible with efforts, joint radio efforts from LOFAR and UGMRT. So 8 years ago, this field was not so, um, how do I say it? Not many were working on it. It was not lucrative, but now it has become very hot topic, as evident from this, because since they have found it to be so big, it is naturally growing into some sort of filament or void. So it becomes a probe of those large scale structures. So you can imagine the scope of it with next generation telescopes. So the future looks very promising using them as probes, and of course to understand their true nature as well. So with that, I'll end and take your questions. Thank you for listening.
Thank you very much, Pratik. Very interesting the topic and also a lot of beautiful images. So let's see if there is any hand up in the online. Any question for Pratik? Okay, we'll start with one then, while people think. So can you clarify me something? So you use the Faraday rotation to measure the magnetic field, and you consider sources, so giant radio galaxies that were behind the cluster for this
supercluster. Yeah.
Supercluster. So with Faraday rotation, you measure the component of the magnetic field along the line of sight.
Yes.
So and you mentioned something very small magnetic field strength, right? You said
Sub-microgauss. Sub-microgauss. Yeah.
Did you subtract? Is there any contribution from the cluster? How do you exclude the contribution from the cluster?
Yeah. So we specifically took those GRGs which are not passing through any galaxy cluster inside a supercluster. So the space between two galaxy clusters. So so it was a very hard problem to spatially locate them, but we did our best to not only, I mean, we took the R500, the virial radius of the galaxy cluster, and we excluded all the sources which are crossing the line of sight of those galaxy clusters. So this is truly intra supercluster medium, space between the two galaxy clusters in supercluster. Yeah.
I see. So you're sure what you're measuring. So if I may add something here also. So did you also try to measure instead the magnetic field strength through other method? I see you have a good spectral determination, for example.
Yeah, so here we did, and here you can see it's around 5 to 10 microgauss, but this is prevalent in the source itself. But there is a very good, because this hotspot, the creation of these hotspots requires an external pressure, the environment, then only there is a shock which is generated, and we believe them to be in equipartition. So once we have the densities of this hotspot, we can have an estimate of the densities outside. Okay, so this is one addition which I didn't talk about. But yeah, if I only talk about the magnetic field strengths, then this is one way to, also do that. But now the first step was to identify them in superclusters. Now we are going to go deeper with more data to, expand.
Okay, but the two values in any case are in agreement apparently of what we obtain in this way. So assuming equipartition and the
yes, yeah. I mean, this is there is a revised and a classical method. So yeah, it's about assuming certain models. So yeah, I've quoted all here. There's an example.
Okay, thanks. Any other question? Felix, yes?
Hi, great talk, thank you. I was wondering, based on what I heard from you in the talk now, it is even with the sample that you have now, it's still not clear if, for example, if the environment is more a factor or the power of the
it's the combination.
AGN.
We conclude that it's the combination of both. It's just not one sole factor. That's the conclusion.
Or do you think that could be more clear with more data? Like, how would you say that you can clarify this maybe a little more even?
No, so we need, so clearly we have enough sample now, almost 5,000, and clearly 25% of them are in a dense environment. So the environment is not the sole cause. The AGN show very similar properties to normal sized radio galaxy. So it's not just that they have exceptional, and the restarted activity that perhaps could be probed more, that they have AGN which routinely switches on and off to efficiently accrete onto the fuel and continue the activity. That is something which can be improved with more statistics. But I think end of the day, it's about sitting down with simulation guys and giving them all the observed properties and then letting them simulate. But it is a very hard problem computationally because simulations so far do it for like few hundred kiloparsec. Here we are talking of megaparsec. So yeah, but I believe it's a combination of multiple factors. We just don't know which is the dominant factor. So
Okay, thank you.
I will abuse more of my chances since I don't see any the other one last question. Since you said that you started collecting also VLBI data of these sources, and you have you also investigated the sources which show restarted activity, where you apparently also have you see this hotspot, secondary hotspot at even more compact scales, right? How do these look like at a milliard second scales? Do you have any idea? Do they look like as these famous compact symmetric objects? These are.
no, you can see this is what
No.
you see. You see
Okay.
this. You see the
So
early signs of. So yeah.
you still have
So
a bright core in any case, right?
that is the condition for VLB observations. You need to have a very bright core because the VLB observations don't work for fainter sources. The telescope instruments haven't reached that sensitivity. So you need a very bright. So this is biased study. This is biased towards bright core radio galaxies or giant radio galaxies. But that is not true. Not all radio galaxies have a bright radio core. So this is sort of biased, but that is the limitation of the state of the art instrumentation.
Well, you know that there are also these compact symmetric objects.
Yes, CSOs.
That are also,
Yeah.
yes. So it's
Some CSOs are giants. Some CSOs have
that
been
was
shown
my
to,
question.
yeah, they are. Yeah.
So there is a link, a connection,
Yes,
right?
yeah,
Because
but very few. There are very few examples. So we need to bring all people together, the samples, study them. But now, if a CSO person who is expert wants to know that if this is a source a giant or not, he's not going to have time to look at the large-scale maps of CSOs. But what he or she can do, is just take the CSO catalog, now cross-match with the GRG catalog and see. Okay. So that's why the importance of creating a sample of GRGs.
Thank you very much. Thanks. Okay, so then let's thanks Pratik again. Thank you very much.
Thank you for having me.
And so I will stop the recording here.